This is the brief on geometric normalization in generalized Laplace operators. So, when physicists are measuring things like heat flow or gravity, using the Laplace operator, they hit a pretty big snag. See, if your coordinate system is curved, your units of measurement can actually stretch or shrink. This is where a crucial geometric correction factor, the metric determinant, or square root of g, comes in to keep all the physical measurements consistent no matter what. So let's break down why this is so important. First, this geometric normalization is a physical necessity. Think about it. In curved coordinates, the actual physical size of a volume element changes depending on its location. This square root of g factor basically acts as the essential stretching factor, correcting for this change so your measurements are always consistent. Second, the whole formula has a really powerful interpretation based on divergence. Divergence just measures how much of something, like a field, is flowing out of a point. Including that 1 over the square root of g factor guarantees the operator is calculating flux per unit of physical volume, and this makes the measurement totally independent of the coordinates you chose. And finally, the math itself confirms everything. To verify this form of the operator, you have to use some fundamental tensor rules. One key identity, that the covariant derivative of the metric tensor is 0, is what proves the whole structure is robust and holds true in any frame. Ultimately, that square root of g factor isn't just some arbitrary math, it's the geometric key needed for the Laplace operator to measure true physical change everywhere.